Hello, class. How are you? Today's online portion is about stem distillation, as you can see here. So let us play the first video. It is mostly
employees
about.
earn at least $15 an hour, but $15 is just the start. That's why.
It is mostly about procedure. Let's take a look at the procedures. They use this big beaker to make this round bottom flask stable, right? The round bottom flask is not stable alone on the table or a hard floor, so they used it. But you can also use cork ring. We have a brownish color cork ring in our labs that's specifically designed for round bottom flask, serving as the base. And we're not using Bunsen burner anymore. It is dangerous. So our setup will have hot plate instead of Bunsen burner, but this can be done in a very safe and very careful manner with the supervision of some, I don't know, expert or something. So here comes water that's supposed to generate steam, okay, for the steam distillation. And you have a bromobenzene, but our case we are extracting natural eugenol essential oil from the dried clover leaves. Okay. So that's a Claisen adapter. This is a condenser that goes here on this branch. When steam and the oil vapor rise, you're gonna have a thermometer holder with a thermometer. So the vapor is gonna travel this manner, and then condenser, as you learned in the distillation, right? We'll have a water flowing from the bottom here and fill up the outer jacket. Internal tube is there, but the outer part will be full of cold water, so the vapors will have condensation. The professor's applying grease for better sealing. It should be done carefully, otherwise you might end up contaminating your compound with the grease. So we don't normally use grease. If you have to, there is a better way of doing it. So don't do the way this professor did. The thermometer head, right, the bulb, where the alcohol or the mercury reservoir is, that should be somewhat lower than this part, the branching part. So the current height is a little bit higher than it's supposed to be. Okay, lower about 1 centimeter more below here because the vapor is gonna fill in and they start to go this way without rising. It's not fully rising sometimes. It just go side away. Then you end up measuring the temperature of the air up here, not the vapor. So as the water flow up, fill up from the bottom, you can see there's no air bubble fully filling up. If you have the water hooked up, you know, opposite way, the water come from the top and quickly flow down, leaving much air bubbles this area and reducing the efficiency of condensation. So the vaporization taking place, there are mixture, but immiscible mixture. So the water and the oil do not make any intermolecular interaction like our discussions in distillation. So the boiling point, right, is not affected by the intermolecular force. They are independent. So water boils independently and oil also gonna boil independently. Although the boiling point of the oil is close to 300 degrees, it has some vapor pressure generated at any temperature. So at the temperature of water boiling, you have a lot less than water's vapor, but you have some vapors of oils rising. And then the partial pressure of the water, that's probably 90 some percent of it, and then a little bit of oil vapors together make up 1 atm. That's when it starts boiling and going against atmospheric pressure so they can rise together. Okay, without the oil, water wouldn't boil yet because it does not have quite 1 atm. How much ever the vapor pressure from the oil, it's going to increase the total vapor pressure to make up 1 atm, whatever the environmental pressure is. After meeting that pressure, it will start boil. So already this part is, as you can see, right? Something's rolling down. That means it's already condensated by the cold water and it's dripping. And the collected distillate is cloudy, meaning you have water, lots of water, and a little bit of oil droplets, tiny oil droplets exist. In the beginning of the collection, you may see just the clear water, okay, because water boils mostly at the beginning. And then raising the temperature to the more closer to the water boiling point, the oil start boiling more, and then you start to see cloudiness because a more significant amount of the oil compared to the before. But yet, water is the main thing coming over. But oil is, in the large amount enough to make the cloudiness. Then, say you are almost done with the distillating off of the oil, then you have only water left. So you will start to see the cloudy, distillates, the droplets start to clear up. Then you know you're done. Then you transfer all the, mixtures. Yeah, you may see some oil layer on top, but that's not everything because you have the cloudiness going on. So that's lots of oil droplets, and you want to recollect. So you want to dissolve oil into the organic layer that's immiscible with water, like we did in the distillation experiment together in person, right? So you pour everything here, and then you're gonna pour organic solvent. So switching the receiver. Our clover case, it's gonna be only around few percentage of the oil from the leaves. But this case, they used more easily evaporating bromobenzene. So they got quite a bit of a bromobenzene along with the water. So slightly different, okay? It depends on what compound you're trying to do steam distillation. So yeah, what was not addressed properly here is the process of separating the mixture. They just discarded everything. So our case, the water and the oil mixture you put in, and then you pour in the organic layer. You can use the dichloromethane we used last time, or anything that's immiscible with the water, but that should be soluble enough for the oil compound. Then you shake it and vent a few times. Then you settle on the ring clamp, wait for the layer separation. Then you got all the oil droplets and the layers you had into the organic layer. Then you drain away the water layer. If it's a dichloromethane, then the bottom layer is dichloromethane. We talked about the density, right? If it's other lighter, less dense organic layer, then the organic will be on top. Say you use assuming you use the dichloromethane, yours is at the bottom. And that's something you want to keep. And top layer is going to be water, you discard. The bottom layer, you have your essential oil and then DCM. Then the DCM will be easily evaporating if you do simple distillation. And then the essential oil that has more than 200-degree higher boiling points than DCM. So most likely you will have the oil remains in the boiling pot. That's the extracted, steam distillated, right? Extracted from the plant. And it normally is out of 10 gram, you should have normally point some gram of the oil. So that's the procedure. Before we go over in depth of theories and procedure, let's watch video number 2. This is giving us some sort of theoretical aspect of steam distillation.
So let's say you have to read an incredibly long email from your boss that you have to finish before the big meeting. Welcome to a brief introduction to the concepts underlying the practice of steam distillation. I'd like to begin our discussion by asking a question, and that is, what happens when two liquids of an organic nature are not miscible with one another? In our discussion about traditional distillation, we always made the stipulation that our binary mixture of liquids must be miscible. But what happens when they don't actually dissolve into one another, at least not intimately at the molecular level? The answer is Raoult's law no longer applies to the situation. So this drastically changes the behavior of our system. And we're going to take a look at this in the coming moments and actually discover that it can be useful that Raoult's law does not apply to systems like these. Let's begin by reviewing how it is that a binary system of miscible liquids is expected to behave. So recall from our discussions of distillation that if we plot vapor pressure as a function of the mole percentage of two components which are miscible in one another, we can plot the vapor pressure of one of those components at the extreme end of the plot. In this case, we'll make this the vapor pressure of component A. If I plot Raoult's law on my diagram, I must start necessarily at 0 for 0 mole percent and end at its vapor pressure with a line. This is Raoult's law for compound A. I can similarly place another compound, let's call it compound B, where its vapor pressure is at the other extreme of the x-axis. Plotting a line gives us Raoult's law for compound B.
So before we continue, let us explore a little bit about the graph, okay? Say the A has a higher vapor pressure. What does that mean? It means it generates vapor so much at boiling. What does that mean? It boils easily. That means boiling point is low. This compound B has a lower vapor pressure at boiling. It means it has high boiling point because it does not generate vapor as well, as easily as A. Then you can see 100% B becomes less and less and less by adding this guy, right? What's this guy? The one that has a low boiling. This is the Raoult's law, okay, when they are miscible. So they influence each other. The intermolecular force influence each other. So as the high boiling liquid gets more and more this guy, right? It happens this way. And for that guy, it happens this way as you mix up more and more. That's when Raoult's law works.
Finally, we can apply Dalton's law to this situation, where we acknowledge that at any particular composition, if we are to take the summation of all the vapor pressures of all the components in the system, in this case just the two, we can determine what the total pressure should be above that boiling mixture simply by adding them. And by doing so, we've generated a plot of Dalton's law for the system. This tells us the total pressure above the boiling mixture at any given composition when it is boiling. Recall again that these two principles, these two laws, were our foundation for making an argument for how we could separate two liquids from one another using distillation. When we're dealing with a mixture of two immiscible liquids, however, the landscape of this diagram changes dramatically. And that's because Raoult's law requires that they be mixed intimately at the molecular level, which is no longer the case. So if we reproduce our plot, but in this case we make the stipulation that the liquids are immiscible with one another, they will establish their own vapor pressures independently of their concentration in the mixture. In other words, these plots will no longer be sloping lines which intersect at zero at the extremes, but rather they will be horizontal lines, indicating that the vapor pressures do not change as a function of concentration. This is true for both compounds A and B.
So the the way they break the bond don't change because they don't mix. Right? They don't mix. So no matter how much A's and B's you mix in to the other one, A stays as A because they're not miscible, right? B stays as a B. So no matter what the ratio is, the intermolecular interaction is the same. Therefore, boiling point same, and the vapor pressure same throughout the different ratios of the mixture.
Assuming that Dalton's law, however, holds in this situation, what we see is that when we plot the summation of the two vapor pressures, is that we end up with a straight line. Now, the potential problem with this is that if we want to isolate these two components, notice that the ratio of components in the mixture above the boiling liquid never changes, which means that by traditional distillation standards, this is not a good technique for isolating these two liquids. And in fact, it is. So we can see clearly that there's a drastic difference in the behavior between miscible and immiscible liquids when we heat them up and boil them. So let's take a look at this immiscible liquid diagram a bit closer and think about exactly what's going on here. What it's telling us is that components of immiscible mixtures establish their own vapor pressures in the flask, regardless of their concentration in the boiling mixture. And therefore, Raoult's law does not apply to such mixtures. This, again, is not a very good observation if it were our goal to separate these two compounds. And so we wouldn't use a traditional distillation to try to separate compound A from compound B. However, this observation will become a useful and valuable observation when we attempt a steam distillation. So let's consider our goal here where we want to separate a water immiscible oil of low volatility from a non-volatile contaminant. And I will just use, again, as normal, we'll use a little cartoon system here to represent these compounds. We'll have blue spheres as water, red spheres as the immiscible oil, and brown spheres as the non-volatile material. So again, our goal in this experiment is to take a mixture of immiscible oils and non-volatile material and somehow isolate that immiscible oil. Notice that water is really not relevant to this process at the moment. All we want to do is be sure that we separate our immiscible oil from our non-volatile material. And in this case of steam distillation, water is just going to provide a medium for us to accomplish that goal.
Okay, as you can see, the setup is slightly different, okay? There are so many different methods of doing steam distillation. There are ways like, okay, making steam in the separate jar by boiling it, and then through the tube, you inject the steam into the extract you want to, okay, the mixtures you have here. Then the steam is going to take the oil, and then same manner, you get the cloudy water solution. Here what we do is it's all same as the previous video, but you have a reservoir of water here. So you can add it, as you need it to add more. Sometimes the water level go down and you need more water, so you open up and recharge the water down here. Or this can start like smoking, partially burning. Obviously, then you need more water. Various reasons you need to have additional water ready. So that's another way of setting up for this steam distillation experiment.
Shown here is a schematic of the steam distillation apparatus that you'll most likely use in a teaching laboratory. The apparatus consists of a separatory funnel which is used as a reservoir for additional water when needed. A boiling flask in which the mixture of oil, low volatility material, non-volatile material, and also the water will be boiled. A thermometer is attached to the device through a still head, so we can monitor the temperature. And you might not be surprised to hear that the temperature in a steam distillation is usually about 100 degrees. From the still head onward, the system is going to look exactly like any other simple still. We'll have a West condenser with the cold water plumbed in through the lower of the two hose barbs and out through the higher of the two hose barbs. We'll have a vacuum adapter to direct the flow of distillate into our receiving flask. Now that we've reviewed,
So the still head is another name for the Claisen adapter or three-way adapter.
how to construct the distillation apparatus, let's take a look at how one functions. We begin the experiment by charging a boiling flask with your materials and a little bit of water. And you'll also add some additional water to the separatory funnel with the stopcock closed in order to provide a reservoir. We'll begin by opening the stopcock very slightly so that the water from the separatory funnel is dripping into the boiling flask. As we apply heat to the boiling flask, the mixture will begin to boil. And of course, as you might expect, water being the most volatile of the compounds within the flask, will get a great deal of water distilling out. But again, remember that the immiscible oil will establish its own vapor pressure in the headspace above the flask, independently of the vapor pressure of the water. This means that if you look carefully, you'll notice that every so often, a little bit of immiscible oil also is carried along into the condenser by moving water vapor. This means that over time, we expect to accumulate in the receiving flask a mixture of water and immiscible oil, which is consistent and very constant in concentration. As we do so, we slowly deplete the immiscible oil in the boiling flask until at some point this process has been carried out to the extent that all of the immiscible oil has been moved into the boiling flask, and now there's only water and non-volatile material remaining in the original boiling flask. At this point, we can deactivate our still and take a look at what we've accomplished. Notice what we've accomplished is that the red immiscible oil material has been removed from the brown non-volatile material using water as a medium. Now, separation of water from the immiscible oil is very simple. That can be achieved usually by liquid-liquid extraction. And at this point, we've accomplished our goal. And this is how steam distillation works.
Okay. Yeah. All right. Here. Where is the color? Okay. So, really briefly, when you have a mixture that are miscible, right? A and the B, they are holding each other. So, say strong, weak charge, they interact. Rather, when they were pure, the strong guy hold the strong, or weak guy hold weak. More boiling point, less boiling point. But in the mixture, strong guy hold the weak guy, and the strong guy and the weak guy, they hold each other. So as you boil, A and the B rise together. We talked about that. What affects the boiling point is actually the intermolecular force between A's and B's. Immiscible case, you can have different ratio, whatever the ratio might be, it's the same thing. A is still with A, B is still with a B. So boiling point of each don't change. How much energy you need to break the bond don't change, okay? In our case, you may have the round bottom flask, right? Round bottom flask. You have water and then other stuff like this. So, don't mind about how they arrange the A's and B's. It doesn't make any difference, okay? So as you raise the temperature, say the bond between A's are stronger, then the B will start going up. And then some point, this will go up a little bit also after breaking this bond slowly with a more heat energy accumulated. Then lots of B's, little bit of A, you add up together, and this becomes total pressure 1 atm. Okay? Then they boil, literally. So bond break is not boiling. We talked about this. You have to break the bond and then go against pressure above. That's why the pressure outside is able to change the boiling point, right? If you lower the pressure, boiling point get lower because you just need to break the bond and easily going up. So you don't need as much heat. If you have so much pressure, then you break the bond. Also, you need to have additional energy to go against stronger outer pressure. So boiling points will go up and so on. So in this case, independently, breaking bond, and then you create lots of partial pressure for low boiling B, and then a little bit of a, gas vapor pressure for A, and then together, if you make the equal pressure to the outer external pressure, then you have a boiling going on. That has a significant effect on total boiling point. Here, for the mixture, boiling point was between strong and the weak because you are breaking the bond between strong and the weak. Here, they're independent and you need to make 1 atm, but this guy makes up 90 some percent of the pressure, but it did not reach the boiling point yet, right? If B is going to boil alone, it should be making 100% of the vapor pressure, but you don't need to. You raise the temperature. Say if this was water, right? You don't need to reach 100. You go like a 98 or something, and you have a very high and very close to the 1 atm. And then whatever is left, point some atm, can be made by the oil at 98. Then together make up 1 atm. So the boiling point became 98, lower than the low one. Okay, so Raoult's law don't work. And also remember in the melting point, you had a weak intermolecular force and the weak lattice energy, so some solid has a low melting point. Over there, if you add high melting crystal, unlike the miscible boiling, like a Raoult's law works, right? The melting point go even lower than the low melting solid, even when you add it high melting, strongly attracting solid. That was the melting. Here is the same thing. You have a low boiling water and you add it strongly attracting but not mixing, right? A. Then what happened? The boiling point went down of the low one, lower than the low one, but you added high boiling liquid. That's the difference. If you add to the low boiling liquid, right, you added high boiling liquid, then the boiling point go up over the low boiling, but less than the high boiling point. So the Raoult's law is behind. So in this vapor pressure curve, if you raise temperature, right, any compound will have a more, as you raise temperature, more and more vapor pressure. When you reach 760, that's the boiling point. For this compound as well, just like oil, as you raise the temperature, more and more oils vaporize. And if you reach 760, then that's the boiling point. And when these are miscible, they reach the boiling point between the low and the high because they attract, right? But for the immiscible case, the pure water boils here at 100, pure oil boils there at higher temperature, then the mixture is supposed to be here if they were miscible because they attract one another, but they don't because they are immiscible. That case, they have a lower boiling point. Like I explained, at this temperature, water already, right, water at this temperature already made up this much of a partial pressure. You only need this much more, right? And at this temperature, your oil has some vapor pressure over here, and that makes up this much additional vapor pressure. So total vapor pressure of the mixture can be 1 atm. So that boiling point, say around 98, below the boiling point of the water, which is lower than this guy. So lower than the low boiling point. Okay, let's switch the gear. Let's pause for a couple of minutes. In an ordinary semester, this lab is boring because you boil really high boiling point liquid, right? So you set up the simple distillation and you add stuff and you boil for 3 hours. So after a presentation and then additional lecture, about an hour, you sit there for 3 hours watching that dripping liquid, cloudy liquid, and few minutes of extraction. And yeah, okay, here we go. Why do we extract things from plants? Not only plants, you know, some exotic froggy or some bug, something, right? Obviously plants as well, but you can extract some useful chemicals for us to heal sick people. Each culture has their own, treasure collections of this type of folks medicine, right? Traditional medicine. So we have something, but these days, say you have a new disease, then you have to find the target, meaning what's causing the disease. Then you design drug that neutralizing or deterring the process of the target molecule. Then sometimes you have that drug in the nature, so you extract them. So you do stem distillation. You cannot do simple distillation, right? If the material is in the skin of frog, you cannot do simple distillation. And also, if your compound has a very high boiling, right, you can't just distill because it may burn. But if you do steam distillation, you can extract that out at 98 degree, okay? Or you can do really extraction with a separatory funnel. You dissolve things in the good solvent like organic solvent or ethanol or water, whatever the good solvent is. You grind them up and then you dissolve them up and you filter off the solid and then you do centrifuge and then you have a liquid. From there, you can do extraction, acid-base extraction or whatever extraction. Okay, that's another possible technique. Or we have a chromatography. We'll do it soon. Okay, depends on which group you are. We'll do soon. So those techniques are there if you have a natural things. If not, you have to synthesize the drug. That's most likely. That's why you are learning organic synthesis in organic 1 and the 2 lectures. Okay, you are making new drug molecule. Starting from small molecules, you add the stuff, you are keep building. Oh no. Oh, okay. Seems like I cannot add stuff. So I can, keep building and building, making new compound. All right. But you cannot just make a one drug because the design is not perfect always. It's just a theoretical. So you are making varieties of similar um, compound, and you are making a lot of we call libraries of candidate drugs. Then we have technique so-called high throughput screening. We have a special test samples in each well. These are the plates or tubes with a lots of little dips, little well like this. Okay, you put little amount of sample there. But variety of different test reagents are there, and then you put your synthesized drugs and then see what signals, positive, negative test result, right? Then say several compounds are qualified for the further testing, then you are saying, oh, we got new lead compound. Lead compound is like a compound has a potential to serve as a drug. Then you do a lot of other tests until it get approved by FDA and so on. So the drug development, right? Like we just said, we go through the process to find the lead compound. Then we go to preclinic and clinical testing. So we do all preclinical testing, starting from just test tube testing or little animal testing or cell line testing, like a petri dish kind of testing, right? And you do all of those before you enter clinical testing right here. So you do phase 1 testing, phase 2 testing, and phase 3 testing. Then you submit for the approval, and then you get the final FDA approval. Then you can sell it. And you heard about phase 1, 2, and 3 these days due to the COVID. So basically, phase 1, phase 0 is like preclinical one or without a human. So phase 1, you deal with a small number of healthy people. Basically, you are checking whether the medicine you made is safe for real test. So you need really healthy individual, even when the medicine has some toxicity for human, right? Because they did the animal test, it may not be very bad, but you never know. Human has a very complex metabolic system compared to other animals. So small number, and you test for toxicity and safety, right? And if you pass this, you go hundreds of actual patients to find whether this medicine actually works. So you check the potency. Also at the same time, you check the dosage, how much is good. But main point is whether the medicine is actually working for human. Then you try thousands of patients with more conditions, okay? Not just that disease. Say ages, right? Genders or races or some other, conditions like diabetes. I have some eye issue, hearing issue, nerve issue, whatever. You have to choose variety of patients, whether they can take this medicine and does not influence other conditions they may have. So phase 3 is very, very important. Genetically, everyone have slightly different combinations of different prehistoric human race, right? In Korea, there are several races with the different combinations of those. So basically, the same drug may not work for all Koreans even. You go to a bigger country like China, India, or the big countries, right? Russia, they have different cases there as well. So you need a big sampling. Then you sell, then you are still doing phase 4. Like, oh, I have these days, you got the shot, and then you have what? Some side effects. So you still are under examination, phase 4. Okay, so stem distillation you can understand in that manner. But here, let's look at our case. When you extract things, say you took plant. Plants have this type of plant cells, right? These cells make layers and layers of uh, sort of polymer that looks like this. And then these make, it could make a cellulose as well. But these are essentially this glucose, fructose, these carbohydrates. But your compound you want to extract is embedded here somewhere or here somewhere. That's what you want to extract out. But the cell has lots of stuff, right? Not just the carbohydrate that makes the wall, but lots of stuff, proteins and nucleic acid and everything there, along with the compound you want to extract. So the extraction may not be as simple as we think. The eugenol, the compound, look at them, variety of activities, useful. One of the places you may already have experience is, dental office. They numb the gum with this. It smells like okay. It's like coffee-ish. Okay, coffee and I don't know, some woody aroma. Yeah, not too bad. Here we go. Eugenol. Vanilla is a little more oxidized form with the oxygen. Eugenol does not have oxygen, instead couple more carbons. So in this molecule, you only have these three atoms that are polar, and there are more nonpolar compound compared to the vanilla. So eugenol is quite oily, nonpolar. Vanilla is a little more polar. Yeah, this is our setup that we use at your college. Now you can understand, right? You saw similar thing that you had separatory funnel connected to this flask directly, but we are using collision adapter here. So you drain water when you need it, and then the vapors mixture and the oil go up and then get condensed, roll down, and this goes to the separatory funnel, right? For the large amount, they do this separate steam generator, and then you shoot the steam into the mixture of the plant, and then you have a condenser, and the more detailed separation of the oil, and they may have a more equipment attached for purification. So the steam distillation might end up separating many, many elements, and you have to check with the other instrument what you have, and then do further treatment for better separation in the purer form before you actually put it on or eat it. So I'll see you guys in the lab again, and have a great one.